собственно, рад представить следующего докладчика. Это доктор Benson. Он является кандидатом технических наук и является доцентом кафедры гражданского строительства Национального университета Chung-Hsing из Тайваня.
Good morning, ladies and gentlemen. Привет. My name is Benson, and I'm currently working for National Chung-Hsing University in Taichung, Taiwan. It's an honor to me to give a presentation today. I mainly want to describe the background of the case we select for simulation and how we use midas GTS NX to carry out a three-dimensional simulation. Here is the outline of my presentation today. I will split them into 5 sections. As you can see from the first one, I will talking about the project background, which I selected for the research, and then we'll move to what are the challenges which we had when we do a real work for this project, no matter in design and construction. And then I'll move to the section of instrumentation, and then to the section of the observation. And I will go into the final part, FEM analysis, which many talk about how we're going to use the midas GTS NX to do a 3-dimension analysis for this top-down excavation. Now I want to very briefly explain the project background. Here is you can see that's the some photos which I took from the research project which we have. This is an excavation for underground stations in phase 1 of Jakarta MRT North-South line. In phase 1 of Jakarta MRT North-South line, it has 6 underground stations. And the station we talk about called Bunahai actually is one of 6, just like I mentioned here. This Bunahai station just beneath this roundabout. It's located in Bunahai at the central Jakarta in Indonesia. And just like I mentioned, that's one of 6 underground stations in phase 1 of north-south line of the Jakarta MRT. And this is and the very special things is this project is a Japan funded project. But in addition to a tier 1 contractor must be Japanese contractor together with local Indonesian contractors. Many subcon or even the consultant actually are come from Taiwan. So this is the first MRT project designed by the engineers from Taiwan. So so that's the reason why you can see when we have a TBM breakthrough, we have we can raise our national flag together with the national flag with Republic of Indonesia together. Because we did have many Taiwanese engineers working there for this project, and that's me. That's my client, Mr. Moda from the contractor side, and my assistant engineer. The whole project actually started to do the design from August 2013. I mean, for so-called notice to proceed NTP, and in March 2019, the whole project opened to operate. And this was a photo which I took last year, 2023, in the entrance of the Bunahai stations. You can see now it is in operation. And I try to continue to give you some further information about the projects which we have. As you can see from the photos here, this excavation actually has 2 parts. The length of the excavation was 430 meters, and the width is around like 20 to 30 meters at the different stations. But actually include 2 parts. 1 cut and cover tunnels and 1 underground stations. And how we're going to do for the excavation, as you can see, the ground, the cross section of the ground profile here. We use so-called top-down methods, which means we have a retaining structure, And once we excavate, we simultaneously we were casting the concrete slab to make it like the horizontal supports. So the whole excavation was done by 5 excavation stages, supported by 4 levels reinforcement concrete slab with various thickness. And the maximum excavation depth is around like 18, almost 90 meters. And the excavation pit was retained using a 1 meter thick and a 24.1 meter deep diaphragm wall. So the interesting thing is, and also you can see the ground here, if you look at the ground profile, it's mostly in clay. And one thing you may note is the penetration depth of the wall is comparatively shorter. As you can see, it's only like a 5 meter. And the main reason is once we actually realized the soil, just like what I showed in my head, the soil is quite stiff. So that's the reason why we can have a comparatively short wall, which we have for this excavation. And also from these photos, please to remember those symbols here. We indicate several locations for the sections which we are going to use for later analysis. As you can see, that's the section DD, which very close to the corner. And we do have one opening, which we use for launch of the TBM. And going north, it has one called section EE, which is much far away from the corner of the excavation. Very important to prove what behavior of the excavation looks like. Important matter is what instrumentations you put on the project site. And the one actually I think here we should use is the wording here is a challenges instead of instrumentation. The challenges is okay for the case which we have here is because this was the first large underground excavation project in Jakarta. So no similar experience which we can refer in the same areas. One issue which we have is absence of the local knowledge and understanding of and the soil informations, because as I just mentioned, this one used to be the first large scale underground excavation project in the Jakarta area. And then, there's reliability data for both soil testing and monitoring, just like what you can see here. This is a result from consultation test which you have, but I don't think the data here can tell you much because as you can see, it's only have a kind of primary consolidation curve. I mean, doesn't have the unload reload curve, so you won't be able to interpret any swelling index which you can calculate the consolidation analysis. And also you can look at the samplers here. This is the tap of the sampler, and suppose this should be a rounded one, but you can see from the photos here is completely twisted, which means, I mean, the ground is much stiffer, but you just try to do your own way to put the sampler in. And this kind of a twisted tap, we believe, cause a lot of sample disturbance, which could possibly reduce the strength of the soils which you have from the testing. So that's what we so-called the unreliable soil data. And here shows the settlement nails which we find from the ground service. As you can see, this kind of a settlement nail system which cannot give you a very reliable data for service settlement measurement. So that's the reason why, to the end, when we do the feedback analysis, we try to ignore all the settlement data. We only take the wall deflection result to do the feedback analysis. And it has a very unique review systems, which the comments given by the review panel are not consistent with what we learned in the past, no matter in theory or engineering practice. And again, very complicated overall environments, which we have to face is also a challenge to us. As you can see from the photo at the central, bottom central, that's the Bunari area, and you can see the whole area was flooded. You can see the car here is all in the water. So we have to face this kind of complicated overall environment when we do the design and construction. So this indeed, cause a challenge to us. And now we actually, the title here should be the instrumentations. Instrumentations which we put here is, you can see what we put here is we put the incrementers in the diaphragm wall and also the strain gauge in the diaphragm wall. And also you can see a strain gauge, in the king post there. And also the surface settlement nails on the ground behind the excavations, though I think the number is quite limited. And this the one at the right, that's the plan view. So you can see the incremental which we have in the DD section, EE section, FF, GG, and HH. Totally we have 5 sections there. EE section is much further away, around like 60 meters away from the corner, and the DD section much closer to the corner. And we also all incrementers in wall are in pair. And you also can see some observation wells, which we can measure the change of the groundwater level. Now I want to talk about what did we see from those so-called observations, what we see from the incrementers. And we first look at the incremental installed at the section EE, which is around 60 meters to the corner of the excavation. Starting from the left, that's the first excavations, and the shape of the wall deflect like cantilever mode. And gradually, once we excavate deeper and we install the slabs, and then you will change to the proper mode, just like this. And you can find the depths having the maximum wall deflection will be more or less similar to where the maximum excavation depth is. And the maximum wall deflection is around 16. I think it's around like that. The red line here is around like 16 to 17 millimeters. And here actually we also try to do some initial simulation based on different assumptions of soil parameters, and then we try using the other softwares, and then we try to compare that with the observation data together. And as you can see, the result which we have from the PMT, the pressure meter test, actually can give us a quite consistent result with the final excavation depth. So that's the reason why in later analysis using midas GTS NX, we decide to use the soil parameters interpreted from the PMT for the simulations. Okay, and now we move into the final element analysis, and that's we first talk about the models. And actually the model is because this is only for an exercise purpose. So I personally will say this model is slightly, I would say, is much bigger than what we expect. So because normally if the excavation length is only like 430 meters, we will add additional like 2 times of the maximum excavation depth, which will be like 40 meters each site, which should be enough. But we use much larger models to do the analysis this time. The length of the model is 1,000 meters, and in this size 500 meters. But if you use smaller your size, the models, you can save the time which you have for the analysis. And we also mark where the sections which we are going to compare later on, D, D, E, E, F, F, and the G, G, H here. And for the figure at the right, you can see that's the ground profile and the excavation depth which we put in our models. Again, in midas GTS NX, it has a very special feature, which is different with others. Is we are eligible to use manually define the mesh you are going to use, and then combine them together. We call that hybrid mesh. So because normally in other similar function, other software having a similar functions, the mesh which you have mostly you only can have some options. Okay, but in midas GTS NX, you can manually change the size of mesh. For example, we use several interval of the mesh. For example, like near the excavation area, we use 1 meter. 1 meter of the interval for to define the mesh size, because that's the area which we need to pay more attention to. But for the place far away from the excavation, we will use a much larger interval, which is like 15 meter, and then we combine these two size of the mesh together. We use the hybrid mesh function in the software. So that's the mesh which we have in when we do the three-dimensional analysis using midas GTS NX, and that's a very special feature this software has. And we just mentioned we use the parameters from the pressure meter test to do the simulations. And talking about the constituted models which we use in these simulations, because this is a stress relief case for excavation. That's a stress relief case. So we choose constituted models in midas GTS NX called modified mode coolant models. For modified mode coolant models, which is eligible to show the characteristic of the soil for stress relief. And this is so which will be more similar to what we have in realities. And these are the parameters we used for the analysis. After explaining the constituted models which we use for the soils, we now move into the structural part. Because this is a top-down case, so the structural members which we need to have in the excavation include the retaining wall, which we have is the reinforcement concrete diaphragm wall, and the floor slab. So both structural members now, which we use the shear element in midas GTS NX. And the shear element actually, what you need to give is, because that's a kind of elastic materials. So what you need to give is just like the strength of the. Basically, you just need to give them the Young's modulus and unit weight and the Poisson ratios. That's what we use for what we use for the structural members. And here shows the boundary condition of the model, as you can see here, and also we need to give the gravity gravity directions move downwards, and you can see that's a symmetric case, and you can see the boundaries there, and also we show what the groundwater levels there, and gradually the groundwater level will be low down to say the almost at the same level of the excavation level. And here is the phase which we put into the construction. And again, we just talking about the function, the special feature of the midas GTS NX is about the mesh size and this is the place where you can define your mesh. And in this slide, it shows the some element size and the and in the models. This slide shows the construction sequence which we have in the models. We actually follow what the real construction sequence which we have in the project site, and try to put them into the simulations phase by phase, so stage by stage. And so you can see we'll start with the diaphragm wall installation, and then we need to, but this case we have a wish in place case, which means the diaphragm wall installation did not cause any displacement. And then we will go stage, you will have the first excavation and then put the deck slab in, and you try to put all the construction phases into here. And these figures here shows the excavation stage up to the second excavation. And then continuing from the previous page, we will have the stage 5 top-down is up to the final stage, which we have the casting of the slab. So that's the case which we have for the construction sequence. Now we look at the result which we have. The blue one is the simulation, and the red one is the monitoring data. And we use the section EE as an example, starting from the first excavation up to the final stage. And as you can see, if we're talking about the maximum wall deflection at the final stage, actually, I think using midas GTS NX can give a quite consistent result with the field observation in the aspect of the maximum wall deflections. But as you can see here, very obvious, looks like the simulation overestimate the deformation above the ground levels, which we consider very likely 2 reasons. One, we may have to change the input of the structural members, especially like the slab. And the other reason is probably we should consider the time effect, time-dependent behavior of soil, which we don't consider in our current analysis. And here shows the surface settlement, which we have from the 3-dimensional analysis, and also the left one is the settlement outside of excavation, and the right one is the kind of a heave, caused by the excavations. And also we try to symbolize them. You can see what we have about the surface settlement distributions. And the other feature which we have about the midas GTS NX is we are eligible to remove or delete the elements on the structural members. If you do remember, we have an opening on the slab. So what we're going to do now is, okay, how to remove some elements on the slab and see how it works, and how it affects the simulation result which we have. That's the place which we can give. You can give the you can assign how to delete elements which you have in the structural members. So as you can see, originally that's the step which we put in, but we try to remove the opening elements there, and then you become an opening on the slab. As you can see from the photos here, that's an opening on the slab, and the dimension is 12 meters times 12 meters. So we just copy this opening into the model. So you can see on the left one, we do have openings there. So we try to compare the results for section HH, which is in a corner but without any opening, and section DD, which also close to the corner of the excavations, but with the openings there. And I just mentioned the maximum wall diffraction at the end from the section EE is around 16 to 17, 16 to 17 millimeters. But if you look at the section HH, it's less than 10 millimeters. And we believe the corner effect of the excavation significantly reduce the wall deflections. So that's the reason why we have much smaller natural wall displacement at the place near the corner. But if you look at the section DD, okay, the displacement became much larger. I mean, from the field monitoring, is even more than 20 millimeters. And we believe this could be possibly caused by the opening of the slab. But even though we try to remove the elements on the slab in order to make an opening on the slab, but looks like we still have a space to improve. I mean, to simulate the similar case with an opening. So I think this deserves some further study in the future. Okay, that's the end of my presentation. Thanks for listening, and it's possible. Thank you.
Уважаемые участники конференции, мы снова в нашей студии. Сейчас со мной Константин. Константин вновь поможет нам с коммуникацией с нашим докладчиком. Здравствуйте, Константин.
Привет, Кирилл. Привет, друзья. Hi, Dr. Benson. How are you?
Hi, Privet. Yeah, I'm good. Thank you. It's possible.
Nice to meet you. Today we got a few questions for you. Are you ready to discuss it?
Yes, please.
Okay. First, I will read the question in Russian, and then I will provide the translation with you. And after then, I will translate your answer into Russian for our attendees. Okay?
Okay, no problem.
Here is the first question in Russian. Какие проблемы возникали при определении параметров грунта в условиях ограниченной информации и как вы компенсировали низкую надежность данных по тестированию грунтов? So, the first question in English for you. What challenges arose when determining soil parameters under conditions of limited information? And how did you compare it for low reliability of soil testing data?
Okay, thanks for the question. My answer for that is if you don't really have a reliable soil testing data, and very likely your simulation is going to be trash in, trash out, because looks like, I mean, not very valuable, I mean, for your simulation. But in case you really need to compensate the low reliability soil testing data, what I would suggest probably two things you can do. The first thing is you redo the soil test with a more reliable method or approaches, which means you need to have a much better quality control to redo the test data, to redo the soil test and get the data, and which also is the way which we did, you know, when we were working for Jakarta Metro project. And the second way possibly you can do is you try to use the field monitoring data, which has to be a reliable one, and then use a numerical analysis to do a feedback analysis. And then probably you can use this way to determine your soil parameters to compensate the lower reliability soil testing data. Yeah. Thank you.
Okay, thank you, Dr. Benson, for your answer. Итак, коллеги, попробую донести до вас мысли доктора Бенсона по данному вопросу. Собственно, первая его мысль была в следующем, что если у вас недостаточно качественные результаты по испытаниям, или их мало, или они плохого качества, то наверняка вы получите плохие результаты вашего расчета. То есть если вы заводите в расчетный комплекс некорректные данные для расчета, соответственно, некорректные данные вы и получите на выходе. То есть trash in, trash out. И доктор Бенсон предложил два варианта для обхода этой проблемы. Собственно, первый — это проведение дополнительных испытаний на последующих этапах проектирования, как они делали в Джакарте на данном объекте. И второй способ — это проведение обратного анализа, то есть на основании полевых данных вы проводите расчет в расчетном комплексе и доводите их до сопоставимого результата. Okay, Dr. Benson, thank you. The next question for you. In Russian. Как решалась проблема с возможностью дестабилизации грунта вокруг основания станции из-за недостаточной глубины проникновения стены диафрагмы? Okay, in English. How was the issue of potential soil destabilization around the foundations of the station due to insufficient penetration depths of diaphragmal addressed?
Okay. Thanks for the question. I think if the excavation is unstable with a comparatively short wall for your excavation, the first things you will see is you are going to have a very large wall choy movement, which means at the bottom of the wall, you are going to have a very large displacement first, and then probably will lead to the collapse of the whole excavation. So that's a kind of a mechanism of the so-called the destabilization of the soils which you have in the excavation. Thank you.
Okay, thank you. I try to translate. Итак, насколько я понял, доктор Бенсон говорил о том, что в случае, если стенка будет терять свою устойчивость, то ее дестабилизация или же разрушение будет первично проходить по нижней части, то есть по подошве стенки, из-за того, что она недостаточно заглублена в грунт основания, и это может привести к последующему обрушению стенок котлована и, собственно, приведет к дальнейшему разрушению всего объекта. Насколько я понял, ответ доктора Бенсона немного не совпадает с вопросом, но, тем не менее, давайте пойдем дальше. Собственно, это его ответ. Okay, and now I guess we have one more question for you. It will be the last
Okay,
one.
please.
In Russian. Как в модели учитывались нагрузки от соседних зданий и транспортных средств на дороге и учитывались ли динамические нагрузки от транспорта? So in English for you. How were the loads from neighboring buildings and traffic on the road accounted for in the model? And the second part, was dynamic loading from vehicles considered?
Okay, thanks for the question. Because so far the current analysis we do is kind of a greenfield analysis, as we don't have a kind of reliable load from the neighborhood buildings and even the traffic. So the current analysis, which actually we are doing the research, so we actually do the greenfield analysis, which means we ignore the impact from all the load on the service, or we don't put them into the model. But in reality, if you do the design and you want to consider those load on the models, you need to depends on what the reality is. For example, if the building is 5 floor or 10 floor, and how many traffics you have on the service, and then you just add into your models. And for the vehicle dynamic load, okay, in order to make the analysis simple, very likely we will transfer the dynamic load into we call that pseudo static load, which is kind of equivalent static load, and you just simply put on the service to represent the dynamic load from the vehicle to do the analysis. That's what we did for the simulations. Yeah, thank you.
Okay, thank you, Dr. Benson. Итак, ответ доктора Бенсона был в следующем, что на текущем этапе они выполняют расчеты в так называемом на свободном поле, то есть они не учитывали в данном расчете нагрузки ни от соседних зданий, ни от транспорта на автомобильной дороге, но при этом у них в планах дальнейшее развитие данного расчета, соответственно, в рамках последующих этапов они планируют для более реального поведения, для описания более реального поведения данного сооружения учитывать вышеуказанные нагрузки. И касательно второй части вопроса по динамике, в данном случае они упрощают динамическую нагрузку от транспорта, они не учитывают ее как динамику, они учитывают ее как псевдостатические нагрузки и приводят к эквивалентным статическим воздействиям. Ответ был в этом. Okay, Dr. Benson, thank you very much for your answers. Maybe would you like to say something to our audience?
Thanks for giving me this chance to present some of my work to everybody, and hope I can see you all again in the near future. Thank you very much. Sebastian. Okay, and bye.
Okay, great. Thank you very much, and have a
you.
nice day. See you next time.
You too.
Bye.